everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Savannah Page. Savannah is a thermal and CFD engineer at Thermal Analytics, where she supports the development and validation of automotive cabin and human thermal models. She specializes in modeling clothing, human thermal regulation, automotive HVAC systems, and medical device electronics, and she has developed a Python tool that streamlines human model pre-processing. Savannah has presented her work at human thermal seminars and conferences worldwide. She earned her BS and MS degrees in biomedical engineering from Michigan Technological University before joining TAI in 2024. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll send you the recording link when it becomes available. And with that, Savannah, if you're ready, you may begin.
Awesome. Thanks for the introduction, Chris. And welcome, everybody. The title of the webinar today is Fast Transient Thermal Simulation for Electronics, Ensuring Reliability and Performance with TAITherm and RapidFlow. So we'll begin with an introduction to electronics thermal management. We'll define the problem, summarize TAI simulation solutions, and then we'll jump right into a case study that will provide some useful background into electronics thermal management. In this first case study, we'll explore how we can use TAITherm in a lumped capacitance model for the electronics components to perform some fast preliminary temperature analysis. And then we'll look into how we can model electronics explicitly in detail within TAITherm to accurately predict the component heat rates, and then apply these modeling techniques to predict the temperatures and derating behavior for advanced driver assistance systems, ADAS cameras, and electronic control units, ECUs, and their components. And in these two case studies, the performance implications of derating will be evaluated, and we will show how these simulations can assist with design decisions. And then we'll close with a summary of key conclusions, a look into what's coming, and advanced features within RapidFlow that can take these technologies further. And then finally, we will close with a Q&A session. So electronics thermal management is critical for a variety of applications, including aerospace, medical devices, commercial devices. But for this webinar, we're going to focus on the automotive applications. And as is often the case, the need for this electronics thermal management and analysis is driven by regulation. And for automotive applications, ISO 26262 is the most critical. ISO 26262 is the functional safety compliance that requires demonstrating that critical ECUs and sensors remain within validated thermal limits, even in extreme environments. A key practice to adhere to temperature limits is to derate the components or operate them below their maximum specifications. However, it's critical to verify that any thermal derating behavior does not affect performance enough to compromise safety goals. So thermal analysis, either via testing or simulation, is used to demonstrate compliance with safety standards in the worst case environmental scenarios. So the role of simulation is to decrease the burden of physical testing, which is time consuming and costly. And shown in this image on the right is the typical V development cycle adapted to highlight the thermal design of electronics hardware, where each stage of the design process has a matching testing and validation phase. Fast, accurate simulation methods can enable early validation studies before the existence of physical prototypes. So in this webinar, we will show how design engineers can use simulation early on in the design process to evaluate electronics component performance. So on the previous slide, we established the motivation for thermal analysis and especially thermal simulation to accelerate the electronic thermal design process. And on this slide, I'll outline the key questions simulation engineers need to be able to answer in order to influence their electronics design. And at the same time, highlight at a high level the capabilities available in the TAI software suite to provide these solutions. So first, an engineer needs to understand how hot a vehicle gets before the electronics power on, so during a hot soak. And of course, how hot the components themselves also get during this time before the electronics power on. So to answer this question, we need essentially accurate, fast thermal soak modeling and realistic modeling of the natural environment. And that includes the buoyant flow physics inside of the cabin, which is something that is notoriously time-consuming. And we also want to see how the electronic components heat up during the operation after the vehicle has been turned on and they begin pulling power and producing heat. So these modeling methods include modeling the component heat dissipation over time as they draw power, modeling any heating through the PCB traces, which can be done with Joule heating within TAITherm, and fast, accurate, transient, thermal, and convection modeling inside the cabin, the HVAC system, and the electronics themselves, and fast, accurate, transient prediction of component temperatures and their derating behavior, which can be done in TAITherm and RapidFlow. We also want to see which of these electronic components pose a thermal risk to safety and performance. So this includes being able to model the derating behavior based on the component temperatures. So how is the power draw being decreased at these high temperatures for these components once they've reached their derating threshold? And then the prediction and extraction of the actual power consumption of the components at those high temperatures versus what they should be pulling in a normal scenario. And finally, what mitigation strategies can improve the design? So this includes the ability to run quickly with RapidFlow and explore multiple design iterations. We'll see that RapidFlow runs very quickly, which is advantageous for running many quick design iterations. So these are some of the key questions that we're looking to answer, and these are some of the modeling simulation needs and what we can do with them. So a key enabling technology for this workflow, as mentioned on the previous slide, is RapidFlow. RapidFlow is a transient flow solver completely integrated into TAITherm, and it was released officially last year within TAITherm 2024.2. And it's not necessarily meant as a direct replacement to CFD, rather as a complementary tool to enable fast, transient thermal simulations earlier in the product design process. RapidFlow is a Navier-Stokes solver, but with some simplifying assumptions to increase speed. The major ones, in VISID, there's empirical modeling of the boundary layer thermal effects. Those are the two main assumptions, and they allow RapidFlow to run on a coarser grid with larger time steps. So you can see the grid for the cabin that we use in this simulation here on the upper right. We use a few different mesh sizes and multiple fluid domains. And the different mesh sizes are between about 10 to 20 millimeters. And we used multiple domains rather than fully connected ones just to make it more efficient for the tighter spaces versus the cabin, which can have a larger mesh size. And for electronics thermal management, RapidFlow enables fast solution of the buoyant flow physics. So you can see in the image towards the upper left, the temperature stratification from the soak simulation. And we can also do fast transient HVAC cabin modeling with TAITherm and RapidFlow. You can see an image towards the left at the bottom from the cooldown case. You can see the airflow coming out of the ducts as it's explicitly modeled within RapidFlow. And the table at the bottom, we see some benchmarking information. On 24 CPUs, the 2-hour soak completed in about 5.5 hours, and the 20-minute cooldown in just under 3 hours. And of course, with higher CPU counts, this gets scaled even further. So other times when I was running this soak and cooldown model on 64 CPUs, the 20-minute cooldown took a little less than an hour, and the soak only took about 2 hours, 2.5 hours to run. So it runs very fast. And this runtime with the soak and the cooldown is about the same for all of the cases that we'll discuss today. And in terms of accuracy, our internal rapid flow benchmarks have shown ability to achieve results within 1 to 2 degrees Celsius compared to conventional CFD, demonstrating a pretty good trade-off between accuracy and computational time. So TAITherm has been a strong solution for a long time for thermal soak using fluid nodes. And in this approach, one can prescribe some level of discretization manually, allowing for some simple temperature stratification in the cabin. So you could have multiple fluid nodes, like one at the bottom, one at the top, to get the temperature difference between them. And this approach is the fastest with an estimated runtime of just over 3 hours for this 2-hour soak example. But RapidFlow enables a significant increase in the solution accuracy, predicting temperature stratification, while only increasing the runtime to just a little over 5 hours on the 24 CPUs. And we can also enable RapidFlow within the ECU and camera components themselves to accurately consider the internal convection. Of course, one could also choose to run the soak with conventional CFD, which generally takes on the order of days rather than a few hours. So there's a few different approaches, but for this one, we're using TAITherm and RapidFlow together. For the cooldown, the cabin airflow is modeled using the RapidFlow solver. Cabin air enters through the HVAC vent interfaces and exits the cabin fluid domain through the recirc interface on the HVAC system. The HVAC system flow is modeled using fluid streams just for efficiency, and the RapidFlow air temperature exiting the cabin domain feeds the HVAC fluid stream temperature. And a PID controller in the evaporator controls the heat rate in the evaporator to target 22 degrees Celsius in the cabin. And the fluid streams through the ductwork then feed the RapidFlow vent temperature inputs. And I'll talk more about this at the end, but I'll tease now that local mesh refinement is coming next year for RapidFlow, so uniform Cartesian grid won't be required. So very soon, resolving the flow through the HVAC system using RapidFlow will be very efficient, and we won't need the fluid streams through the HVAC system. At this point, I want to dive right into our first case study, which looks at how we can use the component junction to case thermal resistance, the R theta JC, to perform a fast temperature screen and quickly evaluate which electronics modules in the current design iteration pose a performance and safety risk. So the real value here is it provides a mean to use the manufacturer data sheets only, any information from there, to estimate the junction temperature from the case temperature. And that is detailed electronics modeling is not really necessary in this case. We just need to be able to predict the case temperature via simulation, and then using the datasheet information, get the junction temperature. And a schematic of the modeling approach is provided below. And in this case, we're only explicitly modeling the case of the electronics module in the thermal model. And the junction mass is modeled as a lumped capacitance with a uniform power dissipation applied throughout, a simple imposed heat. And then by applying the junction to case thermal resistance to that lumped capacitance, we can predict the junction temperature as a function of the case temperature. And if the initial temperature screen predicts unacceptable junction temperatures or long durations above their derating threshold, we can escalate to more advanced 3D modeling and simulation techniques to work with suppliers to identify mitigation strategies, try different components, and quantify the impact on performance and safety. So in the gray box, you can see a representative worst case electronics thermal management scenario for the United States that we're using for these case studies. And we have a vehicle hot shutdown after an extended period of steady state operation, after which we park our vehicle for a period of 2 hours in Phoenix, Arizona. And we pulled weather data from the hottest day of the year this year, which was August 7th. And you might remember on this day, if you were in Phoenix, temperatures exceeded 110 degrees Fahrenheit, greater than 43 degrees Celsius. And you can see historically, this is on the upper end of peak temperature days on record. So after the soak, the driver re-enters the vehicle and initiates a 20-minute cooldown. During the soak, the safety critical electronics modules and the cabin are warming significantly. It's very hot in this car. And then during the cooldown, these components are powering on, adding additional heat through their power dissipation. And in these case studies, we're interested in an ECU, the electronics control unit, that performs some safety critical operation, and it's located somewhere underneath the dash, and an ADAS camera mounted near the rear view mirror. And these components are cooled passively by the HVAC system, so no active cooling. And these components pose the highest risk in the first few minutes directly after powering on. While the cabin air is still cooling down, the cabin air might not be able to sufficiently moderate these component temperatures, especially the ADAS camera, as it's getting really, really hot since it's in direct solar radiation. So here we can see some results from the 2-hour soak. On the left, you can see the overall cabin warming up over time in a manner that is typical for a solar soak from the top down. And you can see very high touch temperatures forming on parts exposed directly to the sun on the dash and rear view mirror, for example. And on the right, I've isolated the ECU and the camera. The camera is getting quite a bit hotter since it's directly exposed to the sun and reaching temperatures between 80 to 90 degrees C, while the ECU is located underneath the dashboard, reaching temperatures in 50 degrees C. And here's some results from the cooldown. You can see on the left, it takes 5 to 10 minutes for the breath level air temperature to reach comfortable levels around 20 degrees C. And then of course, the surface temperatures lag quite a bit behind that. On the right, I've included some images from the 20-minute mark, just showing the airflow streamlines, how the air is moving around the cabin into the HVAC system, and the HVAC surface temperature is colored in this time instance. In vent mode, the dash vents and rear console vents are active, so you can see those ducts cooling down over time accordingly. And the heat rate is applied in the evaporator, so naturally the HVAC system upstream of the evaporator is much warmer than the active vent ductwork. And these soak and cool down results that you see are for all the cases. So for this first case with the simple fast temperature screen, to model the electronics components in a simplified way, we got to have the correct material properties. So the thermal conductivity of the component, which is really important for the material property of the electronic component, can be estimated from the junction to case thermal resistance that's available in the component datasheet. So we have like an example component datasheet here, junction to case thermal resistance, and we can grab that value and plug it into this equation using the area of the component, length times the width, and the distance from the junction to the case, which would be like the height divided by 2, which is this L term. And then that can estimate the thermal conductivity that we can then plug into a material property within TAITherm. And the density and specific heat can also be grabbed from the data sheet, or it can be estimated just based on the material of the component itself. And we can add this new material in TAITherm to assign to the electronic component part, to that junction of the component. And that way the part will have the correct thermal resistance for predicting the junction temperature of the component based on the case temperature. And to make it simple, a lumped capacitance part can be created to model the junction of the electronic component inside of the case geometry. So we can set this to use the new material property that we just created, and we can impose heat based on the typical power consumption of the component from the data sheet. So you just add the imposed heat to the junction component. And then for realistic thermal conduction to the circuit board, in this model we use another lumped capacitance part that's thermally linked to the case geometry of the component. And the conductor for the thermal link can be calculated as the inverse of the junction to board resistance found in the component datasheet. So again, looking at the example datasheet, there's the junction to board thermal resistance. We take the inverse of that, and that can be used as the conductor for the thermal link between the board and the case geometry of the component. And then we can connect the case of the component to the surrounding rapid flow fluid. And in this case, it's super simple. There's no derating or current curves. And the simple setup allows the simulation to run quickly, helps us get a feel for whether these components will work well for this scenario, or if they will have decreased power draw from the high temperatures. And if the initial temperature screen does show that some of them are past their derating threshold, then we can use some more complex modeling to run multiple design iterations to see what can be done. So here are the results of the simplified temperature screen. We see that during the cool down, the component junctions of the image sensor in the ADAS camera system and microcontroller 2, and also microcontroller 3, but I'm just showing microcontroller 2 here in the ECU, surpass the derating threshold temperature in the simplified temperature screen. So both these components derate at 85 degrees Celsius, and you can see that they are passing that derating threshold quite quickly and stay above it for the majority of the cool down. So these components are at high risk of poor performance due to these high temperatures. So that was the first case study. We showed how we can use the simplified approaches to electronics modeling to perform fast temperature screen for the various electronics components. So once we've identified those problematic components, that image sensor, the microcontroller 2, and the ECU, then we may want to work with suppliers and internal design engineers to identify specific mitigation strategies, such as derating the components, switching out to different components, changing the position of the control units. And in these cases, we may want to do some more detailed modeling of the PCB, explicitly modeling things like the other components, the other capacitors, microprocessors, traces, and the heat dissipation and derating behavior of all of them. So the image on the left shows the detailed ECU model used in case study 3, for example. And there are two main methods for modeling the various components inside the electronics module. And the first method is just using the simple power derating curve from the manufacturer datasheet, like above here. And we can apply this directly to the component of interest using a user routine to predict the power dissipation as a function of the temperature and the voltage that they're drawing at that time. And we can also use a second method with lookup tables from a manufacturer datasheet or from your own data that you have on the power dissipation of the component for a specific temperature range. And from there, a user routine can find the current and voltage being used by that component at that time, and then get the correct imposed heat to apply to that component based on also what temperature the component is at that time. So there's a few different ways to apply derating behavior to the components. But for these next cases, we are considering derating. So we want to make sure that we get the board materials correct as well. And a standard double-sided PCB has 2 layers of conductive copper with a thin layer of solder mask covering them and a thick middle layer of an insulative substrate. So in TAITherm, we can model these layers using copper, FR4 material set to the correct thicknesses, and then a high surface emissivity of 0.9 can be set to the front and back faces to model the thin solder mask layer on the board surface. And the electronic component material can be chosen to have the same thermal properties as specified by the manufacturer from your own data, like I showed previously in the simple case. And these material properties for the board layers or the components themselves can always be modified to match whatever material is actually being used. And the surfaces of both the component and the board that are in contact with each other, their junctions can be parted out and set to the correct material properties, whether that's copper or lead solder. and then they can be thermally linked together to create conduction between the component and the board. And the junction to board resistance of the component can be used to calculate the conductor of the thermal link. And similarly, the copper traces on the surface of the board can be parted out and have the correct material properties. So they have the copper surface instead of a solder mask surface. So in the second case study, we're looking at how we can use this simulation workflow for advanced driver assistance system camera design, and how we're comparing the derating. Here we're comparing the derating performance of two image sensors, which is one of the most temperature sensitive and impactful on the camera performance. And we saw from the simplified temperature screen that it's getting really hot, and it is past its derating threshold. So when an image sensor is thermally derated, the image sensor frame rate can be reduced, can cause latency, delays in detection, and pedestrian recognition, which can obviously have serious safety implications. So we're looking at performance and safety for these two image sensors, and both are low power CMOS image sensors designed for automotive applications. The first is an image sensor front on semi, which has an operating temperature range from -40°C to 105°C, but it's actually only functional up to 85°C. And the manufacturer recommends not using the sensors above 85°C as it reduces the image quality pretty drastically. So the typical power consumption of this device is around 290 milliwatts, depending on the ambient light conditions. And the second image sensor that we'll be looking at is from ST Micro, and it has an operating temperature range that's larger, from -40°C to 125°C, and a typical power consumption of 145 milliwatts, so has a smaller power draw than the first sensor. So we would probably expect some better performance from the second image sensor. And both of these image sensors begin linearly derating their power at 85°C. So this slide describes the modeling of the ADAS camera system. We chose to focus on the most important part of the ADAS camera, the image sensor. It's the most temperature sensitive component, as temperatures outside of its functional operating range can reduce image quality and resolution. So it's less likely to detect incoming obstacles like pedestrians or oncoming traffic. And a lookup table was created for the image sensor, imposed heat, based on the power dissipation at various temperatures from the manufacturer datasheet. And the other components included in the system are like some larger inductors, smaller passive components, and these are modeled with user routines calculating the imposed heat based on the current and voltage pulled by the component, as well as the temperature of the component themselves. And derating was considered in this model. So if a component reaches the derating threshold specified in the datasheet or based on the operating temperature range, then the power dissipation will decrease by a certain percentage based on how hot it is. And this model geometry doesn't have any traces, but we assume that they would have a little thermal effect on the more important components. And here we see the results of the two different image sensor components. So the components in the ADAS system start very hot. They start at around 75°C, and they heat up as the electronics begin operation. We see that both image sensors surpass their derating thresholds, which were the same, 85°C. But the second image sensor actually reached higher temperatures. And even though that second image sensor does draw less power, it heats up more than the first image sensor because of its smaller size. And the smaller component has less surface area for the heat to dissipate through convection to the surrounding air, so it ends up holding onto the heat, and the junction temperature is about a couple degrees higher than image sensor 1. Here's a snapshot of the temperatures at 3 minutes. Here you can clearly see the size difference between the two image sensors, and that the one on the left, image sensor 2, is hotter than image sensor 1. So yeah, this size difference ended up having a larger impact on the temperature of the component. And you can see that the case of these components get quite hot during operation. And on this slide, we've plotted the total power dissipation and load of each image sensor compared to 100% of the ADAS load. So at 100% load, the board would be pulling about 0.77 watts with image sensor 1 and about 0.67 watts with image sensor 2, right? Because there's a difference in the typical power draw that they require. And because of the high temperature environment in the camera module, we see that both image sensors have reduced power consumption due to derating. And both image sensors dissipate almost the same amount of power with derating. But what's more of interest is how much power they dissipate compared to their typical power load that's needed to function properly. So image sensor 1 gets down to about 72% of its typical power load, which you can see on the graph on the left. And in comparison, image sensor 2 only gets down to about 82% of its typical power at the lowest. And this makes sense as the first image sensor requires more power with a smaller operating temperature range. So it's derating more quickly. And the linear slope for derating based on the manufacturer derating threshold and operating temperature range is steeper than the second image sensor. So the practical effect of this derating is that image sensor 1 is going to have a lower achievable frame rate and increased noise than image sensor 2 will. It'll be probably blurrier, and the system may be more unable to detect potential obstacles or pedestrians. So in this case, even though image sensor 2 did end up getting hotter, it still has more of its power load compared to its typical load. So in this design iteration, we'd probably want to go with image sensor 2 still. So in this next case study, we're comparing the effect of the location of the ECU under the dash on thermal performance of the electronics module. We saw that some of the microcontrollers in the electronics module are at risk of derating, and we can see how that compares based on where the module is actually located under the dash. So this type of study can be done very quickly in TAITherm, requiring just a simple geometry translation in the TAITherm GUI on an external tool. And in the base case, the hot case, the ECU is located underneath the dash in a region that's closer to the hot dash, that's under high solar loading, and further away from the HVAC recirc intake, thus receiving significantly less passive cooling from the HVAC system. So we would expect this to be a lot hotter than in this cool case where it's next to the intake. And here we see the modeling of the ECU. We chose to model some standard components that would be part of most types of ECUs, not picking a specific one, including some RAM, multiplexers, flash memory, buck converters, analog to digital converters, and the manufacturer data sheets, including their derating curves, operating temperature, typical current and voltage values, were used to create lookup tables for the power dissipation based on the current voltage and temperature of the component at that time. And the less influential passive components, like resistors, are also modeled using a user routine based on their power dissipation and derating behavior. So again, derating was considered in this model. So if they reach their derating threshold, they'll reduce their power draw by a certain percentage. And some of those key components that we saw in the simplified temperature screen are microcontrollers 2 and 3, as they were much higher than their derating threshold temperature. And the heat created by current moving through the PCB traces was also modeled in this case using the Joule heating feature within TAITherm. And this feature uses a script that calculates the localized heating of a trace or a bus bar based on the current or voltage drop between the trace terminals. So there's different terminals connecting to the components, to the traces, and then to the next components, and that difference in voltage or the current going through it allows us to calculate the heat of those traces. Here we can see some temperature animations of the ECUs during the 20-minute cooldown phase. The animations are on the same scale, so we can see right away that the base case is significantly hotter than the cold case. And plotted above are the peak temperatures on the highest temperature microcontrollers on the PCB, those microcontrollers 2 and 3. And in the hot case, temperatures peak between 80 to 85 degrees C between the 5 to 10 minute mark. And we can see that in the cold case, the junction temperature peaks in the first 3 minutes at only about 73 degrees C. And then it continues to decrease rapidly to less than 60 degrees C during the 20-minute cooldown. So this change in location of moving it closer to the recirc intake had a significant effect on the peak junction temperature for these microcontrollers in the ECU. So we would expect much better performance from this control unit being in a more passively cooled region. And here I'm showing some streamlines colored by temperature for the cool case, and it's quite obvious why this is a much more advantageous position for the ECU. You can see in this position, it's receiving significantly more cooled airflow as the air travels toward the recirc intake. And on the right, just showing again the difference in temperatures at the 3-minute mark, highlighting that the temperature difference here is very significant between these two different locations. And again, plotted the total power dissipation for each of these cases. And the red is the ECU operating at 100% load. We can see that it pulls just over 2.2 watts for both the hot and cold cases. And the cool case is plotted in blue. We can see some derating was happening for approximately like the first 5 minutes of the cooldown, but the ECU was still operating at over 98% peak power. So the effect on performance there is not expected to be significant. On the other hand, the base case, we can see significant derating occurring for essentially the entire 20-minute cooldown. So the ECU is operating at 85% of its peak power for the cooldown. And the thermal throttling in this case had a significant impact on the performance of the ECU. And these fluctuations that you see in these graphs were due to some convergence issues with some of the more passive components. But you can follow the trend of the power load and see that it is drastically reduced in the hot case. And assessing the impact on safety is a bit more nuanced. Really depends on the nature and the function of the ECU. And that being said, it's definitely possible that safety objectives are at risk of being compromised at this degree of derating for this ECU module. For example, due to reduced data processing speeds or latency. So pretty drastic difference between these two cases. So in conclusion, TAITherm and RapidFlow, they enable a unique simulation workflow for electronics thermal management, able to model the buoyant flow physics and the HVAC flow and cabin cooldown. And we also see that a simple lumped capacitance approach using the junction to case thermal resistance from manufacturer datasheets can be used to identify which electronics may pose a performance or safety risk. And then we can model those high-risk components explicitly within TAITherm to see their heat dissipation and derating behavior. And this proposed simulation workflow can be used to evaluate the ECU ADAS performance in detail and perform rapid design studies. And this short runtime that RapidFlow allows can let you run like the full soak and cooldown model in only about 6 to 7 hours. So you could run this full soak and cool down iteration, like 1 per day, which is pretty remarkable. So it allows for fast design iterations. And finally, I wanted to highlight some advanced features within RapidFlow. Coming soon in 2026, moisture tracking and moisture transport will be available within RapidFlow. And this can allow us to predict fogging on the ADAS camera films, which is commonly reported as an issue. And this can also impact performance of the camera. And also coming in 2026 is local mesh refinement. And this will enable efficient modeling of the HVAC internal flow field. So like I said, in these cases, to speed up runtime, we use fluid streams inside the HVAC ducts to model the airflow in them. But with local mesh refinement, it will be possible to efficiently use RapidFlow to model the air in those ducts as well as in the cabin. And 1D coupling with RapidFlow is already available. It's possible to integrate a 1D vehicle thermal management system that can help evaluate liquid cooling systems for larger electronics models. So there's lots more to come and many cool features that are already available that can allow for more advanced design iterations for electronics thermal modeling. And here are all of my references. There are quite a few of them. And I wanted to say thank you for attending this webinar. And now I'm going to open it up to any questions.
Yeah, thanks, Savannah. So we can take some questions here. Are the component capacitance values, resistance values, et cetera, taken into account?
Yes, so I don't think I touched on this in the webinar, but those are taken into account in the user routines that set the imposed heat for the components. So for like the capacitors, their capacitance is taken into account when calculating their power dissipation. So their AC and DC power dissipation is used to calculate the imposed heat of the component. And within the AC power dissipation, the capacitance is used. So yeah, for each of the components, that's an input into the user routine calculating their imposed heat.
All right, thank you. Did you use RapidFlow for the area underneath the dashboard when looking at the ECU?
Yes, we did. There's RapidFlow under the dash, in the cabin, and in the ECU module case, and in the ADAS module case.
All right, thank you. How are the HVAC fluid streams connected to RapidFlow?
Yeah, can I go back to that slide that shows them?
Of course.
Okay, let me go back there. Probably easier with a visual again. Okay, so we have the air coming in through the recirc, and it enters. It's basically like an outlet in RapidFlow that it's going out of, and then that fluid temperature of that part is an input to the fluid stream that is in the recirc. So the fluid temperature of the outlet RapidFlow part sets the temperature of the next fluid node for the HVAC system. And then it uses all these fluid nodes and fluid streams throughout the HVAC system to move the air through it. And then it connects back to RapidFlow at the vent interfaces. So the last node of the fluid stream, and these are using user routines, the last fluid node, the temperature of that gets set as the inlet temperature of this vent in RapidFlow. So their input parameters in the RapidFlow configuration file, and a script for each of these different vents sets the inlet temperature of that vent to be the same temperature as the last node in that fluid stream for the vent, if that makes sense. So it's connected by scripts that take those fluid temperatures and assign them to the correct inlet. temperatures.
Thank you. What other applications could this electronics model be applied to?
Yeah, so yeah, this was pretty focused on automotive, but we see in a lot of other areas, like I have more of a background in medical devices as well. And within that, for like wearables, wearable electronics, you really want to make sure that the components aren't heating up too much during high usage. So maybe somebody is outside in really hot weather and they're wearing a smartwatch that is working overtime because they're running and it's gathering their data. Then in a case like that, this would be a great application for these exact same modeling techniques. So you could see if those components within that smartwatch are getting too hot and could potentially burn the person. So there's a number of different applications that these could be applied to, and you could use the exact same modeling techniques with whatever components are inside of those different devices.
All right, thanks. Looks like that'll do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email later today containing a link to watch the recording of today's webinar session. Again, thank you all. Thank you, Savannah, and everyone have a nice day.
Thank you.